All right, so aside from having to listen to my own voice, things seem good. So here we are, we're at this point, and the landscapes hopefully is a better picture. So here we are. So we're sort of stuck because we have two unknowns and we have one equation, and that's insufficient. So here's where I would ask if you have any ideas, but I'm talking to myself, so I won't. Hopefully you should at least be considering what we've learned about most recently, which is angular stuff. And, you know, torque and momentum and kinetic rotational energy. So all that stuff is great. Obviously, we're not going to be doing any kinematics here. K-rod, there is no K-rod because nothing's rotating. There is zero angular momentum. Nothing is changing in the system, so that won't help. What will help is torque. So this problem becomes essentially, well, we are also going to have to consider torque big time. So let's do that. So here's our setup, and what we know is that the net torque is 0. Because it's not spinning, which would be really, really strange if it were, but it's not. So the net torque is 0. So this is going to enable us to solve the problem. So we know it's not spinning, and we can tell hopefully that it is not spinning around any arbitrarily placed fulcrum. So you can place your fulcrum wherever the heck you want. It really makes no difference. To me, I think maybe the first logical and wrong place to put the fulcrum is probably at the center. So let's take a look and see what happens if we do that. So if you do place the fulcrum at the center, so we place, you know, our little fulcrum, which, you know, make it a little seesaw. If we place it there, we will have a upward force due to leg 1. There will be a downward force due to gravity from mass A. There is an upward force from leg 2. And there's a downward force from gravity acting on mass B. Okay, so what's the problem here? Well, I mean, probably not all that apparent right away. It doesn't seem like anything is all that wrong with it from the beginning. But the problem is, this will again get us back to having two unknowns. So if you consider that object with respect to this fulcrum right here, we have 4 torques exerted. We have the torque that results due to force 1, the torque resulting from force A, the torque resulting from force 2, and the torque resulting from force B. We know that the net torque is 0, but we don't know F1 and we don't know F2. So we're still going to end up with an equation with 2 unknowns. And technically, you actually could solve it this way, but I won't. You could solve it this way because we'll end up with the second equation for, we'll get our second equation that includes 2 unknowns. We'd have 2 equations with 2 unknowns. So this could work, but this is not going to be the easiest way to do it by any stretch of the imagination. So we are definitely not going to do it that way. Also, I'm just going to orient. So since we can place the hinge wherever we want, the hinge or fulcrum or whatever you want to call it, we can place it wherever we want. Easiest place to put it is going to be somewhere such that F1 and F2 do not affect the torque. See what I'm saying? Remember, we've seen pictures like this where there is a horizontal force acting on a circular object, but it exerts 0 torque because it wouldn't cause the object to spin. So we're going to use that same kind of principle to place the torque in a more effective and make our lives easier sort of position, which will be either at leg 1, or at leg 2. I think the easiest place to start is probably leg 1. I mean, that's where I would probably start. That seems most obvious. I mean, you could place it at object 2, and to be honest, I'll probably show both solutions, but the easiest place to put it is object 1. That's probably most apparent. So if you place our fulcrum at object 1, what we're going to end up with is, so there's our fulcrum. There is a torque that exists due to the gravitational force on object A. There is a torque that exists due to the gravitational force on the table. There is a torque in the opposite direction that exists due to the upward force of leg 2. Then there is another torque that exists due to the gravitational force on object B. So this is where we're going to start. And with most of these problems, and some of them will get trickier than others, so it's never a bad idea to consider like sort of a number line, like where you arrange these different masses and consider the numbers. In this case, it's going to be easier, but in the second one, it's going to be really helpful when we look at the solution if you place it at leg 2. So let's do that real quick just to set up. We know that our number line is 6 meters long. We know that object B exists 1 meter from the edge of the table. So object B exists at the number line of 5 meters, like the position of 5 meters if we're considering the number line. The force 2, which I'm going to have to call F because the numbers get confusing, exists 2 meters from the edge. So this exists at 4 meters with respect to our 0. And really, I mean, just considering the number line now with respect to 0. So the center mass of the table occurs at the halfway point, which is 3 meters. Object A occurs at 1.5 meters. And the whole reason I'm doing this, I probably should have said this from the beginning, but I didn't, and I'm not re-recording, is because torque equals force times the distance between where the force is exerted and the axis of rotation. So this L is the distance from where the force is applied to the axis. In this case, here's our axis. So the L, the distance, is just going to be it's measured on the number line, which is pretty straightforward. In this example, it will be less straightforward in the second. So well, what? Well, let's find some torques, huh? Yeah, let's find some torques. And first of all, we should talk a little bit about the direction. Since object A, the table, and object B, with respect to this axis, would cause our since it would cause things to spin, this isn't going to do what I wanted to, but it would cause things to spin like that. Well, not exactly like that, but so it won't do what I want, but that's okay. I don't know how you get to what I want. But anyway, they would all cause it to spin clockwise. So the torque that exists due to object A, the table, and object B, that would all cause clockwise torques, which is a negative direction. So torque A, torque T, and torque B are all negative. The only positive torque that you would have is the torque that exists due to the support force of leg 2. So this will be our positive torque. So basically, our positive torque is going to equal the sum of our negative torques. So what we should do here is find those torques. So the torque that exists, due to object A is going to be equal to the gravitational force on A times the length, the distance between where the force is applied and the axis. So in this case, that's going to be MA times G times L, I guess I'll call it A, not just because I'm a Dodger fan. So the torque that exists due to A should work out to be 132.3 Newton meters. The torque that exists due to the table, going traveling horizontally, the table comes next. So Ft times the L, in this case it's the mass of the table times gravity times the distance between the table's center of mass and our fulcrum. That should work out to be 705.6 Newton meters. The torque that exists due to object, I guess the next thing you would run into is force 2, but since we don't know force 2, I'm not even going to bother calculating it just yet.
Mr. McGee, please call 6103. Thank you. Mr. McGee, 6103.
So torque B is equal to the gravitational force on B times the distance between where it's applied and the axis. So in this case, that's the mass of object B times G times, L, we'll call it LB. It should work out to be 343 Newton meters. Again, these are all negative, so technically, yeah, I probably should be considering them negative, but so really you have two options. Just a very quick aside. We haven't really done things like this, but you could say that the net torque equals 0 equals the sum of all the torques. And that would, in order to do it like this, you would need to treat these like negative torques. We usually don't do it like that, just because I guess I don't usually do it like that. So what I would do instead, and you're going to end up basically with the same result anyway, I would consider it more like the torque that exists due to force 2 is equal to the sum of the other torques. And again, I'm just, the negative signs, I'm not crazy about them. So I would just set it like this, whatever, you end up getting the same result anyway. So torque 2 is the sum of these three torques, and torque 2 should then end up being 1180.9 Newton meters. So that is going to be something I'm going to take with me to the next page because I need a little room. Okay, so that we know is our torque 2. We also know that torque 2 is equal to the force 2 times the length between the leg 2, the second leg, and our original hinge. And hopefully you can tell that since this occurs 2 meters from here, the distance is 4 meters. We already talked about that here. So the distance is 4 meters between F2 and our hinge. So what we don't know is that. So F2 is going to equal torque 2 divided by L2, or 1180.9 Newton meters divided by our length 2, which is 4 meters. So F2 should end up being about 295.225 or whatever newtons, because it's a force. So this is F2. And if you remember way back to equation 1, where we saw that the sum of force 1, the sum of our two forces, our two unknown forces, F1 plus F2 equals 392 newtons, all we're going to do is reuse that, and we are done. So given that F1 plus F2 equals 392 newtons, F1 is going to equal that 392 newtons minus F2, given that F2 is 295 newtons, F1 should work out to be 98 newtons. 97 newtons. 97 newtons. And that'll do it. Those are our forces. We're done. So this is the second and last type of mechanical statics problems you need to be aware of for the take-home quiz that you'll have to work on, hopefully over the weekend, if not early next week then. So that's it. Problems do get a little tougher, as you'll see on the homeworks, but not much, not a whole lot. All right, cool. So that's an easier way to solve it. If you check out the next video that I'll post, I'm going to do the same thing I did here, except I'm going to place this fulcrum, actually weren't attached, I'm going to place my fulcrum at object 2, which is going to have some weird repercussions. And it may help you out for some of the harder problems, so I'm going to go ahead and do that one too. All right, thanks.